This video is about the dot product. As always, begin by reading carefully through the textbook and taking some good notes, but now consider the following highlights for this topic. We'll begin with a definition of what's called the dot product. Of course, we're in the context of vectors and we've been establishing properties and things with them already, so we're going to keep using that. By definition, for this dot product, if we have vector u in component form, so with components a1, b1, that would be the horizontal and vertical components of vector u, and then let's say we have vector v with its components, so a2, b2, respectively, so those horizontal and vertical components. If we have those vectors u and v, then their dot product, denoted by vector u and then a dot and then vector v, is defined by the following. Now, just to note, the dot is not a brand new symbol for mathematics. If you've taken algebra before, then you've used the dot for multiplication, such as, 3 dot 2 means 3 times 2, right? So we've already been using this kind of symbol before, but now it means something more specific in the context of vectors, and that's why we're calling it the dot product for vectors. Now, here's how we can define it. U dot v, vector u dot vector v, equals the product of their horizontal components. So with the ones we've defined here, it would be a1 times a2. And then we add to that the product of the vertical components. So it's a1, a2 plus b1, b2, where you're multiplying those components together. a1 times a2 plus b1 times b2. Now, let's take note then. If these are just numbers, right? These a1, b1, a2, b2, these are just the component form numbers representing the horizontal and vertical components of these vectors, then you're really just getting a number out of this, right? So note this product is a real number, or you could say scalar, as we're used to using by now with that definition and that language. It's not a vector. So this result, a1 times a2 plus b1 times b2, will produce some kind of real number. You can call that a scalar, but it's definitely not a vector that's in any kind of component form. It's just a number. Now, there are some properties of the dot product we want to note as well. One of them being that vector u dot vector v is equal to vector v dot vector u. In other words, they are commutative, you could say. This dot product doesn't have an order that matters. You can switch the order u times v or v times u. Secondly, you may recognize some of these, again, back from algebra. The second one being more like the associative property. So if you have grouped with parentheses, scalar a times vector u, that's just scalar multiplication, but then you dot product that grouped scalar multiplication with vector v. So in parentheses, you have scalar a times vector u, and then we're dotting that with vector v. Then it turns out that's equal to a couple other options. You could group the vector dot product and then put the scalar out in front of it. So it's like a, the scalar, times, in parentheses, vector v dot vector u. You're just kind of grouping a different set of them. Or you could even put vector u in front and then dot product that with the parentheses containing scalar a times vector v grouped together. Again, that may look familiar as the associative property of multiplication, back from the algebra days or real number days. If we go to the third one, then this again looks kind of like the associative or distributive property, actually. So if you have grouped vector u plus vector v in parentheses, but then you have a dot after that with vector w. So you're taking the grouped sum of vectors u and v in parentheses, and then you're saying dot some other vector w. Well, it turns out it's almost like you can distribute that vector w to both of the vectors inside the parentheses. So the result would be then vector u times, or dot, that is, vector w plus vector v dot vector w. And notice the order here. You're just distributing vector w into each of those vectors on the inside, and that's the result we get. Or fourthly here, if we take the magnitude of vector u, remember denoted by what looks like absolute value symbols, and you square that. So you're squaring the magnitude of vector u. Turns out that's equal to vector u dot vector u. In other words, you can dot product a vector with itself, and the result is the same as squaring the magnitude of the vector. So we'll see some examples shortly of doing some actual arithmetic with these, but these are just the properties we want to keep in mind with them. Let's add a note as well that if theta is the angle between two non-zero vectors, then the following are true. So we're going to have several properties coming out of this situation, but we're just kind of defining that theta is the angle between two non-zero vectors. Now, the first of these is what's called the dot product theorem. So a theorem, of course, is a provable proposition in mathematics. You've seen these before, likely, in various contexts. Well, there's something called the dot product theorem, which says this, that u dot v, so vector u dot vector v, is equal to the product of their magnitudes, so the magnitude of vector u times the magnitude of vector v, times the cosine of theta. Remember, theta is just this angle that's between these two non-zero vectors. Now, typically a textbook will have a proof of this theorem. That's not too difficult to follow. I recommend reading through that in the book. It typically involves the law of cosines, which is familiar to us. Nonetheless, we can assume and use this result of the theorem. Secondly, we could talk about the angle between two vectors in the following way. So remember, we're using or assuming that theta is this angle that's between two vectors, as defined above. And if so, then the following is true. The cosine of theta, that angle, is equal to a fraction whose numerator is vector u dot vector v, there's the dot product, and whose denominator is the product of those magnitudes of those vectors. Okay, so again, cosine theta, theta being the angle between these two non-zero vectors, is equal to a fraction whose numerator is vector u dot vector v, and whose denominator is magnitude of u times magnitude of v. So we can use that as a formula, which can help us find an actual angle if we know something about these vectors. And lastly, we have the theorem of what are called orthogonal. The theorem of orthogonal vectors. Now, you may or may not have heard the word orthogonal before. It sounds fancy, but it really means something pretty clear. Ortho means right, literally means right. You may have heard of an orthodontist or orthodoxy or something like that. Ortho is just a prefix that means right. And then this second word for gonal would mean angles. So it's right angle vectors. That is, two non-zero vectors, u and v, are perpendicular if and only if their dot product is 0. So right angles, of course, perpendicular means that something meets at a right angle. And so that's true of vectors u and v if and only if, means it has to be true that their dot product is 0 if they are perpendicular, or if they are perpendicular, then their dot product is 0. Those two things necessarily go together. All right, let's spend a little time on some examples that now use these definitions we've defined above. So for our first example, this one has two parts. It says find A, in other words, part 1, vector u dot vector v, that's a dot product as defined above. And then part 2, B, also find the angle between vector u and vector v to the nearest degree. So we're finding two things for each of these, and we have a couple sets of those to work with. So part A gives us vector u in component form. Component form, of course, remember this is with the pointy parentheses that we've seen and used. The first horizontal component is 3, the vertical component is -2. So vector u is the vector 3, comma, negative 2. Vector v is the vector 1, comma, 2. So horizontal component 1, vertical component 2. So let's start with example 1a. We'll do part A. Of course, part A in the instructions here was to find the dot product. So we want to find vector u dot vector v. And we have the definition above, and we have the components given for these vectors. So as we discussed above in our definition, you can go way back up in here and see that the dot product of u times v would be their horizontal components multiplied together plus their vertical components multiplied together. So that's all we're going to do for now these given vectors, which would mean 3 times 1, that would be the product of their horizontal components, plus the vertical components would be negative 2 times positive 2. So we simply do this arithmetic to get 3 plus a negative 4 for a final result of negative 1. The result of a dot product is a number or a scalar. It's not a vector. So that's our dot product. And then part B for this example 1a said to find the angle between these two vectors. Now we have a formula for this we're going to borrow. If we just go back up, there it is. Above in our notes, we have an angle between two vectors formula we can use. So we'll just bring that right down with us. It's the one that involves the cosine. So to write it in place here, we have the cosine of theta equals this fraction whose numerator is the dot product of u and v vectors and whose denominator is the product of those magnitudes of those vectors. So since we already know this some of this information, let's plug it in. We know that then the cosine of theta equals the numerator is just the dot product of u and v, which we just found. That's the negative 1. And then we're going to have to go back and remember what the magnitude formula is. You may recall, let's put this in here just for reference. So recall the magnitude of vector u, we discussed magnitude before, is the square root of a squared plus b squared. That would be those component form values for that vector. So for this one, the magnitude of vector u would be the square root of 3 squared plus negative 2 squared, which of course be the square root of 9 plus 4, so the square root of 13. So we can put these in place now. We have the magnitude of vector u as the square root of 13. I'm not going to write out the lengthy form for the magnitude of vector v, but it would be found the same way. Look up at the components of v. If you square each of them and add them together, 1 squared plus 2 squared would be 1 plus 4, or in other words, 5. So the square root of 5 would be the magnitude of vector v. Now, what we're saying is that the cosine of theta is equal to this value, negative 1 over the product of the square root of 13 times the square root of 5. We want to find theta, though, the actual angle between them. So what we're going to have to do is now use an inverse trig in order to compute this with the calculator, which we should be able to do. As we've already seen in using inverse trig functions, we could now say then that the angle theta, if you take the cosine inverse of both sides, on the left side, of course, the cosine would cancel, giving you just theta. But then you'd be left with theta equal to the cosine inverse of the right side, which is now this fraction we just computed of negative 1 in the numerator and square root of 13 times square root of 5 in the denominator. So this is something we should be able to approximate with a calculator. Let's go ahead and break out a graphing calculator and punch this in. If we turn it on and punch it in as said, so we have second cosine will give us a cosine inverse. And then in that input, we want to put this fraction we have, which has a negative 1 in the numerator. So I'll put in negative 1, then divided by. Now remember, with these graphing calculators, you'll want to keep the entire denominator in its own set of parentheses because it has more than one piece. So I'm going to now open up a set of parentheses for the denominator, which contain second and then square root of 13. And then I'll move out of that square root and then multiply by, so times. And then I want second, another square root, this time 5. Now be careful with parentheses as always. I'm going to close the parentheses that contain the denominator of our fraction, which is really just the product of those two roots. But then I also have to close the parentheses containing the cosine inverse function. So always double check on those parentheses, and if you get an error, go back carefully and make sure that's not the issue. Let's now make sure we're in the right mode, so we'll probably go with degrees in this one. Let's hit the mode key, make sure you're in degree mode. It might be in radian by default, but if we're in degree mode, we'll now hit enter and do this calculation, which gives us, it looks like 97.1 degrees approximately. So we'll call that our result, 97.1 degrees, and that's what we're getting for theta, which is part of what this question was asking, the angle between the vectors. Okay, let's move on to example B, still within the same problem. So this is example now 1B, same instructions, which has two parts. Of course, find the dot product and then find the angle between. But in example 1B, now they're giving us a different set of vectors, u and v, and they're not given in the component form with the pointy parentheses, but rather they're given in the ij form. Now, as we know already, they're synonymous in terms of the way you can represent them. So if I have vector u given as I plus 3j, which is how it is, we know that that actually means in component form 1 comma 3 in terms of the pointy parentheses ordered pair setup, right? So if you prefer to use that or just want to reference what these all mean, that might help just to write down. Vector v is given as 4I minus j. Well, in the same way, that means it's in component form 4 comma negative 1. So if we have the components we need for these vectors, then we can just put them together to get these results. So part A is to find the dot product. Well, in this way, then vector u dot vector v, as noted earlier, is the product of their horizontal components plus the product of their vertical components. So that would be, in these vectors, 4 times 1, or 1 times 4, plus 3 times negative 1. And so put those results together, you'll get 4 minus 1, which is, 4 minus 3, 4 plus negative 3, which is ultimately just 1. And for the second part, part B, we want to find the angle between these vectors. Well, we already recalled the formula in the previous example, so we'll just kind of use the same thing here. We know that the cosine of theta, this angle between the two vectors, is equal to a fraction whose numerator is the dot product we just found. That would be just now the number 1 for this example, over the product of the magnitudes of these vectors. Well, we just reviewed the magnitude formula for the previous example. You're going to add up the square of those components, but then take the square root of the result. So for this one, in the same way, that would give us the square root of 10 as the magnitude for vector u. That would be 1 squared plus 3 squared inside a square root, 1 plus 9. And then for the magnitude of vector v, again, this one given as components 4 comma negative 1, you'd square each of those and add them up. So 4 squared is 16, negative 1 squared is 1, so we'd have 17 under the square root. So square root of 17. And this is what the cosine of theta equals, which means then theta would be the cosine inverse of this very result, 1 over the square root of 10 times the square root of 17, as previously noted. And we can approximate this on the calculator. And it looks like the result this time is about 85.6 degrees. Well, let's move on to another example. Number 2 says, determine whether the given vectors are perpendicular. Well, that word should sound a little bit familiar. So we have two examples here, so 2a and 2b. Each of them is giving us components for or values for vectors u and v. Let's recall above what we said about perpendicular vectors. In point E above in our properties, we said that in the theorem of orthogonal vectors, orthogonal meaning right angle vectors, two non-zero vectors u and v are perpendicular if and only if their dot product is 0. Well, we've been finding dot products, and we can continue to do that just to determine if the dot product is indeed 0 for these. So let's find that. In the first example, we're given vector u in component form as negative 2 comma 6, and vector v in component form as 4 comma 2. So let's compute the dot product of these two vectors to determine if we have orthogonal vectors or not. If we use the formula for dot product, we'll be multiplying their horizontal components together. So that's a negative 2 times a 4. And then we'll be adding that with the product of their vertical components, which would be 6 times 2. Again, just coming directly from where these vectors were given. Of course, negative 2 times 4 is negative 8. And then 6 times 2 is 12. Now, negative 8 plus 12, of course, is 4, which is not 0. So we would say, no, these are not perpendicular, because they would have to be a dot product of 0 to be perpendicular. It's that simple. Let's try this second example. This one's given in ij form, but again, we could, if you'd like, rewrite it in component form. The first vector u is given as 2i minus 8j. Well, that's the same as 2 comma negative 8 in component form. Vector v is given as negative 12i minus 3j. Well, that'd be negative 12 comma negative 3 in component form. And so now let's do the dot product on these. U dot v would be the product of their horizontal components. That would be 2 times negative 12 plus the product of the vertical components. That would be a negative 8 times a negative 3. If we simplify these, we'll have negative 24 plus 24, positive 24. So negative 24 plus 24, of course, is 0, which means we would say yes. These are perpendicular because of the orthogonal definition we have above. Their dot product is 0. That means, of course, if you were to graph these two vectors, what you would find is that they would meet at a right angle. That's exactly what that means to be orthogonal. All right, let's do one more example. This last one, number 3, says to find, and then there's an expression given which has parentheses containing vector u plus vector v, and then that set of parentheses is connected with a dot to a second set of parentheses which contains vector u minus vector v. So we're going to put together the pieces of this that we know. We have vector addition or subtraction going on inside each set of parentheses, and then we have dot product connecting them. So let's just break this down one little step at a time. Vector u plus vector v would be, and by the way, these vectors are given in ij form. We have vector u given as 2i plus j, and vector v given as I minus 3j. If you want to just look at the numbers in that ij form, or write out the components, which would be for vector u 2 comma 1, and for vector v 1 comma negative 3. Either way, you have to get at those numbers to use in these definitions. So if we start with the sum of the vectors, that is vector u plus vector v, you may recall all you're going to do is add their corresponding components together. So I'm going to add the horizontal components of 2 plus 1 to get 3 for this new vector, which I'll also write in component form, comma, and then the horizontal or the vertical components added together of 1 plus negative 3 would be a negative 2 for the vertical component. This is, again, just the vector u plus vector v that we're doing. In fact, I'll even coordinate these maybe with some different colors. The second expression we'll do here as vector u minus vector v. I'll put in a different color. Of course, we're now going to dot product this result together. So our second result here would be vector u minus vector v. Again, subtraction of vectors means just subtracting their corresponding components in order. So 2 minus 1 would be 1 for their horizontal component, comma, for the vertical component, 1 minus negative 3 would really be 1 plus 3, or 4. And so the component form of the difference of these vectors, vector u minus vector v, would be the vector in component form 1 comma 4. Ultimately, we're trying to find now the dot product of these two resulting vectors that we just got from the addition and subtraction. Of course, dot product, as we know from above, means you multiply the horizontal components together. So for these, that would be 3 times 1, the horizontal components of each being multiplied together. And then we add the product of their vertical components multiplied together, which would be a negative 2 times a 4 coming from those components listed here. Ultimately, then we'll have 3 times 1 is 3, plus negative 2 times 4 is negative 8, so you could really just say 3 minus 8, which of course would be negative 5 for the result of that dot product.